All right, you guys. So here's the video on lost signs. This is where trig really starts to expand its horizons, right? So far we've only looked at trigonometry inside of a right triangle. We're going to expand it outside of that now to any triangle. I'm going to put a little asterisk there. We're not going to look at sine of acute angle, or of obtuse angles yet. So we're not going to take like the sine of 100 yet, but we're getting there. All right, so law of signs, big idea here is we already have this this in the past without numbers, right? So in one triangle, the biggest angle is across from the biggest side, medium across from medium. So here, if this angle was the biggest, that means that this side is the biggest. Whoops, I wrote side. And that goes both ways, right? If you find the biggest side, and then if this is the medium side, that means this is the medium angle, and this smallest angle will go across from smallest side. So we already had that relationship established in the past. Now all we're going to do, the new here, is we can now just attach numbers to this, okay? So with numbers, we can now solve for missing unknown sides, and this applies to any triangle. So if I find the biggest side, just to show you an example, right? If I come across a side of 20 here, and I know the angle opening up to it, and then I know the angle opening up to an unknown side, I could use that relationship now with the sine function, with trigonometry. I could use that large across from large, medium across from medium, right? I know the side across from 50 is going to be bigger. I could guess, I don't know, 30, but I could actually use the sine function to calculate that missing side. And the reverse is true, right? If I know 71 degrees is across from 15, then the side across from 10, the angle across from 10 has to be smaller. Now I could take a guess. It could be like, I don't know, maybe 50 degrees, like just wild guessing. But I could actually use the sine function to establish an exact value for that. And that's where we're going today, okay? So with no further ado, let's look at it. The law of sine, super easy to remember. In a triangle, it is literally the sine of an angle divided by the side. So the ratio of the side length and the sine of this angle here, that ratio is true for every angle and side in a triangle, right? So the sine of angle A divided by side A is equal to, and the sine of B divided by B is sine of C divided by C. Super easy to remember and incredibly useful for finding missing sides and missing angles in a triangle. Okay, so let's just do it really quick. All right, so what I get here is the sine of 30 degrees divided by the side it is across from, 20, is equal to the sine of 50 degrees divided by, the side it's across from, let's just call this x because that's what we're looking for, and so is divided by x. And so that simple ratio now turns this problem that in the past, all we could do is look at this triangle and be like, well, this is 100 degrees because there's 180 degrees total. So I know this is bigger than 20. And I know this is biggest side, so it's even bigger than that other one. And that was as far as we could go with geometry so far. Now, though, we can numerically calculate that side, and we're going to get into in just a second why the law of sine works. But right now, all I'm going to do is show you the algebra really quick. If I want to solve for x here, you could cross multiply, so you get x times the sine of 30 degrees. Remember that the sine of an angle is just a single number, equals 20 times the sine of 50 degrees. So the way I see this problem right here, like off to the side, I see this as like 3x equals 5, right? It's a number times x equals, and this is just a number, right? 20 times sine of 50. Looks a little scary, but it's just x times a number equals a number. So if I want to solve this, over here I divide both sides by 3. So in this problem, I just divide by whatever number is multiplied by x. So I'm going to divide by the sine of 30 degrees, divide by the sine of 30 degrees. All right, and the answer is x equals 20 times the sine of 50 degrees, all divided by the sine of 30 degrees, right? And then you just punch that into a calculator. Little side note there, sine of 30 degrees, you know what the sine of 30 degrees is. That's one of our special right triangles, right? Like if I draw it really quick, here's a 30, 60, 90, across from the smallest side, across from the medium, across from the biggest. So the sine of 30 degrees opposite over opposite over hypotenuse from SOHCAHTOA, sine of 30 degrees is just 1 over 2. So I could actually put that in here. This is just a 1/2, right? So divided by 1/2 is the same as multiplying by 2. So actually x is 40 times the sine of 50 degrees, right? That's just, you could do that part. Now I'm going to try and swipe over here on my fancy iPad and try and type this in. So 20 times the sine of 50. That didn't work. It went, there we go. So 20 times, oops, let's use an x for that, the sine of 50 degrees, all divided by the sine of 30 degrees. Boom, there we go. So it came out to 30.64. We knew it was bigger than 20. That's a check in terms of logical. Okay, and then just to double check, I'm going to trash that, and I'm going to say, what about 40 times the sine of 50 degrees? What's that come out to be? And again, we got the exact same value, right? Because the sine of 30 is that. Okay, so we got 30.64. Oh, got to go back the other way. There we go. So we get is around approximately 30.641, and then whatever we were supposed to round to, we'd round to that value. Okay, so now doing it in reverse here, we'd say, okay, so let's look at this. We know that this one's across from there, this one's across from there. Let's call this y, so we're just dealing with a different variable. So we get that the sine of 71 degrees over the side it's across from, 15, is always equal to the sine of this unknown angle y all over the side it's across from, 10. Okay, so if I want to solve for this, I'd multiply both sides by 10 just to get rid of that denominator. Okay, and then I'm going to get that the sine of y is equal to, and here I could simplify this a little just to 2 and 3. And so I get 2/3 of the sine 71 degrees. Now, keeping in mind, again, this is just a number, right? So really what we have here is, whoops, switch pens. Really what we have is the sine of y equals a number. Okay, so let's just pretend it's 5. It's absolutely not. But the sine of y actually can't be bigger than 1. So let's just say it's 0.5. So if we want to say, okay, I know what comes out of the sine function, I want to go backwards. I want to find out what angle went into it. That's exactly what the inverse sine does, or the arc sine. So I'm going to go ahead and erase this. Actually, I'm going to erase that whole thing. Okay, so rewriting that exact same statement using an inverse trig function, we get y equals, and this, I'm going to use arc sine. You could use sine to the -1, same thing. And then inside the parentheses here, I got to say 2/3 times sine 71. Let's see how my calculator gets arc sine. So 2/3 sine of 71. Let's see which way I'm swiping here. There we go. Okay, so we got the arc sine of 2 times sine of 71 all over 3. Let's see what that comes out to be. Boom, 39 degrees. Let's go back and see if that's a reasonable answer. So we get that y is around, and I'm just going to round it to 39 degrees right now. Let's look back up here. Is that reasonable? Oh yeah, we guessed 50. We overshot it. It was 39 degrees was across there. So that's how you use it, both to find an angle and to find a side, okay? But now the question is, why does this work, right? Oh, Mr. Lawyer, you just made something up. I mean, that's a cool trick, but why does it work? So let's just take any old triangle here. Specifically, I'm working with an acute triangle. It makes the solving a little easier. The only reason I'm avoiding an obtuse triangle right now is you run into this problem of if you have the sine of like 100 degrees, and we haven't really gone into the unit circle yet. And a trick we need to use is if you have an angle bigger than 90, what you end up doing is you end up getting the sine of this, whatever angle it is, let's say it's x, is actually equal to the sine of 180 minus x. And I just don't want to get into that right now. It's true. This formula absolutely works for obtuse triangles too. It just uses some information we haven't introduced yet. So let's stick with an acute triangle because every step is there and we had done it all before. Okay, so looking at this triangle, we don't have any right triangles. And up until this lesson right now, we could not use trig outside of a right triangle. So let's make some right triangles, okay? So the easiest right triangle to make here is let's just drop down in altitude straight down. Boom. And because I chose an acute triangle, that altitude's inside. So it's not outside. That was the difficulty we would run into the other way. So I'm going to label this, I don't know, like height, okay? Now what we can do is just write a couple expressions here. Well, one expression in this left triangle is, I could say the sine of angle A is equal to h over b, right? Just opposite over hypotenuse. But in the right triangle, I could also say the sine of angle B is equal to the height over A. Now, anytime you have more than one variable and you've got two equations, that's a system of equations, and we could combine those. And so I want to keep, just to highlight here, I want to keep the A and the B. I want to keep the B and the A. I want to get rid of this H. Okay, so the way I'm going to get rid of that H is I'm going to use some substitution and combine these two equations into one, and I can get rid of that extra H, okay? So let's solve for H in both of these, and so I get H equals, just multiplying by B times the sine of A, okay? But that same height, right, this is one triangle, that same height is also equal to A times the sine of B. Now, since it's the same height, we set those equal, and so we get B times the sine of A equals A times the sine of B. And that right there, that is the law of sines. It's just we could rearrange it to be a little more elegant so we don't have A's and B's on one side. Let's put all the A's on one side and all the B's on the other. So what we're going to do here is we're just going to divide both sides by AB. Okay, on this side the A's cancel, so I got rid of the A's. This side, the B's cancel, and what I'm left with is the sine of A over A equals the sine of B over B. Now, if we want to expand this, all we do is we rotate the triangle. We don't even need to rotate it, actually. I mean, let's just do it in place. All we would do is we would just draw this, call this some letter other than H. Let's call it, I don't know, W. And we do the exact same thing. The sine of C is W over B. The sine of B is W over C. Beep, boop, bop, beep, substitution. And we get, so the exact same steps we just did with a different height. And we get the sine of B over B equals the sine of C over C. And then we just chain these together, right? The sine of A over A equals the sine of B over B, which is necessarily equal to the sine of C over C. So that's it. It's just a height in the triangle and using the sine function more than once and then combining them using system of equations. So super cool trick. I mean, it took us just a couple minutes to do that, but now we have this amazingly elegant, simple to remember formula called the law of sines, okay? Now that we've done that, I just want to warn you, don't assume, right? You remember when we did ASS and we were talking about congruent triangles? ASS isn't enough to know two triangles are congruent because it leads to ambiguity. This third side, right? If you know this angle and you know this side is congruent, that's not enough to know the two triangles are the same because that third side here, this 160, could swing and it could make a triangle here or a triangle here. So we could get two, it narrows it down from infinitely many triangles to two possibilities, but it does give rise to two different scenarios. So if a problem like this came up, which it's not going to in this book, we haven't covered this material of the sine of angles bigger than 90 and how they relate to the sine of angles smaller than 90. But I just wanted to mention that. So when dealing with the ASS, if you know the triangle is acute, which is what we're going to do on all of our problems in this section, then you don't need to worry about this ambiguity. But later on, okay, in this class and in future classes, we'll expand trigonometry using the unit circle. And now we could take the sine of 3,000 degrees, the sine of negative 500 degrees. And once you've expanded trigonometric functions to a bigger range of values, it does give rise to this ambiguity and something to be aware of. And it all comes back to that ASS from congruent triangles. Okay? But you can forget it for now. That will not come up in any of our problems. Okay? All right, so let's just do a couple examples here. This one says find the area of each. So this doesn't even use the law of sines. This is just a useful application, right? Well, if I need the height of a triangle, or I mean the area of a triangle, it's 1/2 base times height. That means I need the height, right? So I'm arbitrarily going to choose one. I could drop it this way or this way. Doesn't matter which one you choose. I'm going to choose this one. Okay, so now that gives me the sine of 65 degrees is h over 29. I could solve for the height of the triangle by multiplying by 29, and I get the height is 29 times the sine of 65 degrees. Okay, now we're just going to plug that back into the area formula here. So the area is equal to 1/2. The base, if I chose this as my height, then this must be my base because they're perpendicular. If I had chosen the other height, so in pink, if I chose this to be my height, then this would be the base of my triangle. So you could have done it either way. You'll still get the same area either way. And then we'll go back here. So we get the base of our triangle is 25. And the height of our triangle is 29 times the sine of 65. Now I'm going to leave that up to you to calculate. I don't want to keep switching between the calculator. So that's the answer. Now over here it says find the area of this polygon here. Now we don't have any triangles. The whole chapter, right, is about triangles. And the way we investigate any shape, regardless of number of sides, is by cutting it into triangles, right? Even in computer graphics and everything's cut into triangles, okay? So here, we basically have two options, right? I could cut it this way, but the bad plan is I don't know how I split that 78. I don't know how I split that 100. Like how many degrees are on one side and how many degrees are on the other. I've just introduced a lot of variability here and a lot of uncertainty. So that was a bad plan, okay? The only other option is cut it this way. Oh yeah, this is great. Look at this. Now I've got multiple sides. I've got multiple angles. I mean, this is fantastic. All right, so as I was saying, this basically now you cut two triangles into exactly this scenario, and then you just add the two triangles together. Okay, so really quickly here, let's drop in altitude this way. We've got the height is the sine of 78 is equal to the height over 124. The height is 124 124 times the sine of 78. Sorry, I just got a little typo with my pen there. And then we've got the base, and so the area is equal to 1/2 the base, which is 115, times the height, which is 124, times the sine of 78. There we go. Okay, and then we have the second triangle. Now this is the problem, okay? So if we take this thing, we try and cut this way, again, we've now gotten into this problem of I don't know how much of the 100 is in each triangle. So that's not the way we want to draw the height. So the other height, you might go like, well, we're drawing it this way. But this is an obtuse angle, so we don't draw it on that side. The height here, instead, when we have an obtuse triangle, we expand the base out, and then we draw it this way. So here's a right triangle, right? And if that's 100, then this angle right here is 80 degrees. This is our height, right? And so, yes, this is a new scenario, right? The height is outside a triangle, but it's still a right triangle. We still know the length of the hypotenuse is 104. So let's go down here. Let's go the exact same thing. The sine of 80 degrees is equal to h over 104. Solving, we get h is equal to 104 times the sine of 80 degrees. And then we get the area of that triangle is 1/2. The base, again, this height is perpendicular to this base. We don't include this little bit sticking out of the triangle. That's not part of the base. So the base is 95, and then times the 104 times sine of 80. Okay, so that was a little more complex of a problem, but not too bad. All right, now it just says find some missing sides. So now it's just direct application of the law of sines. So missing sides first, because we're not using inverse trig for this. So just like the examples we did before, so the sine of 52 degrees is, and then you divide it by the side it's across from, so it's over 28, is equal to the sine of 79 degrees over w. We can cross multiply, so w times sine of 52 equals 28 times sine of 79. Dividing by this number that's multiplied, our coefficient of w, we get w is equal to 28 times the sine of 79 degrees all over the sine of 52 degrees. And again, those are all just numbers, so you can punch that into a calculator. Okay, and then I'm leaving that again. I'll leave that up to you guys to just plug it in. Here, though, we have to find the angle, all right? So we're using the law of sines here. So sine of 42 degrees. And just really quickly to go back here, we know that there's 180 degrees in this triangle. So we could find this missing angle, 180 minus these other two values. So those add up to 120, 131. So this is a 49 degree angle. So we could then use that 49 degree angle to find this missing side. Let's call it x. So we actually have enough information to find every piece of missing information. This isn't just like we can find one side. We can unlock the entire triangle this way, which is really powerful, okay? So down here, we got the sine of 42 over 29, because that's what it's across from, is equal to, and there isn't a letter here, so I'm going to say the sine of angle A over, and then it's across from 36. So multiplying by 36, I get that the sine of A is equal to 36 times, and again, when you multiply by 36 on both sides, it becomes 36 over 1. So it's 36 times the top, 1 times the bottom. So that 36 ends up on top of the fraction. Just some simple pre-algebra review there. Okay, so that's what we got. The sine of A is equal to that. That's exactly a call for now the inverse trig function. So if the sine of A is equal to that number, then the measure of angle A is equal to the inverse sine. This time I'll use the sine to the -1 notation. It's exactly the same as the arc sine of 36 times the sine of 42 all over 29. Okay, so that's the measure of angle A. But then the nice thing is, once we find the measure of angle A, that gives us this angle, 180 minus, and we end up getting this angle, which then we can use the law of sines to find that missing side. So once we start using the law of sines, we can now complete the entire triangle from any combination that made triangles congruent. So SSS, SAS, ASA. So once we start using this, we can really start unlocking all these separate sides. Actually, sorry, SSS is the one we haven't gotten to yet. If we start with SSS and want to find the angles, that's the time when we use the law of cosines. And we'll get to that. Okay, so let's look at a word problem now from the chapter. Okay, so we got this, and it tells us this is an isosceles triangle, and it says find the missing lengths here. This is a real Fort James. I've actually been there on an 8th grade trip. That was fun. Okay, so here let's first find the missing angle here. This is 46.5 degrees, just subtracting from 180. So this is the isosceles triangle's base angles, which means this is, which means this is 300. Wow, we already got one of the missing sides. That is good. Okay, and so now to find the other missing side, we apply the law of sines, which is the sine of 87 degrees to the missing side. I'm just going to call it AC equals And then let's do either one because they're the same ratio. The sine of 46.5 to 300. Cross multiplying, we get the side AC times sine of 46.5 equals 300 times the sine of 87. And then dividing, we get AC equals 300 times the sine of 87, all divided by the sine of 46.5. Okay, we got one more problem here, and then we'll call it a day. And here's the last problem we're going to do today, so just take a sip of coffee. So this is a tree growing on a hillside. The key here is that it's talking about the 16-degree angle to the horizontal, and my pen is turned off for a second here. So the 16-degree angle to the horizontal and the 68-degree angle to the horizontal. So remember that anytime we measure angle of elevation or angle of depression, it's always from the horizontal. So it's saying this hillside goes down 16 degrees. So we can put that same 16 degrees here in this triangle. And then 68 degrees is, if you followed this line up, that would go to the sun shining rays down. That's what's causing the shadow there. But we always measure that from the horizontal. But we could complete finding all these angles then, right? In this triangle here, height is always perpendicular to the horizontal. So we've got this triangle, that's 68 degrees and 90. So the leftover is 22 degrees. And then in this bottom triangle, I got to kind of blow this up. If that's 16 degrees and a right angle, then the rest is 74 degrees. So we have every single angle in this triangle. If we only knew a single side length, right? So we got 22 degrees, we've got 74 degrees, and this here was 68 plus 16, so we get that 78, 84 degrees. Okay, so that's our one like non-right triangle to deal with. And oh, lo and behold, we know the shadow is 18 meters. So now this becomes just a law of sines problem. Notice that without the law of sines, you could have approached this directly. So I'm going to erase some of these numbers here. You could have approached this directly by just saying, okay, well, this 16-degree angle goes here. And then I could use just right triangle trig in this right triangle to say, okay, 16 degrees and 18. I could find this piece of the height, and I could find this length. And then I could say, okay, well, in this top right triangle, as a totally separate step, I could say I could use this angle and this known side length to then find this piece of the height. And then it says, what is the height of the triangle? And all I would do is just add these two pieces together. So we could have directly approached this with the two right triangles, and that's what we would have done in the past. But now we've combined, we actually use that exact trick, drawing the altitude of a non-right triangle to come up with one elegant formula. So let's use that elegant formula over here. In this triangle, we are looking for the height, and so we simply say, okay, well, I'll do it in green, because who doesn't love green? So the sine of 84 degrees over the height equals the sine of 22 degrees over 18. Cross multiplying, h times the sine of 22 equals 18 times the sine of 84. Dividing, we get h is 18 times the sine of 84 degrees, all divided by the sine of 22 degrees. Okay, I hope you enjoyed that video on the law of sines. The next video will be the law of cosines.